Hello, thank you for joining me today at our talk, Top Endpoint Threats. My name is Irina Adamski. I'm Director of Research for Cortex XDR with Palo Alto Networks. And I will be talking to you today about the top endpoint threats that we've seen in the past year and ways that those can be detected and prevented. So, we will be talking about four types of attacks about .NET Server exploits and Java Server exploits. We'll talk about driver abuse and open source and commercial hacker tools that we've seen being more popular with threat actors during the past year. So let's dive in and get right to it. The first topic is the rise of .NET vulnerabilities. This has started back in 2021, not just in 2022, but in 2022, we've seen more and more Exchange vulnerabilities, such as proxy not shell, such as the OYSSRF vulnerability, and others come into light and being used in the wild by multiple threat actors targeting multiple organizations across all geographies and all verticals of industry. So you can read more about it in our Unit 42 blog, but let's talk about what really happened there. First, I'd like to do a quick recap of what is an SSRF vulnerability. So it's a server-side request forgery. Basically, the attacker is capable of using a application on the server to make requests that it is not supposed to be doing. So this way, the attacker is able controlling the app and getting into places in your network that he shouldn't be talking to. Those are unintended requests. Basically, he can do whatever he wants if he is able to have the authentication and the access point to your server. In the past year, we've seen multiple chained vulnerabilities, such as proxy logon, which had a pre authentication SSRF, and then one of either file drop or deserialization exploits used in after it got the access to the network. Proxy not shell, also a pre authentication SSRF vulnerability. Then there is an internal privilege escalation that allows you to get more privileges in the network, and then a file drop, allowing for a web shell to be created and getting persistency on the network. Then the next one is proxy not shell, which was very similar to proxy shell, but it's not proxy shell. So this is where the name comes from. Again, it's a post authentication SSRF. So in this case, the attacker already needed to have some credentials for the network, and it couldn't just get to your network or your server unauthenticated and exploit it. And then another deserialization vulnerability, which allows you to execute code. The last one we've talked about and we've seen in the past year is OYSSRF. It's very, very similar to the proxy not shell chain because the second part of it is the same deserialization vulnerability, the same exploit used in both cases. The difference between proxy not shell and OSSRF is basically that there is a different SSRF vulnerability in the first stage of the attack. And in the first stage, we're using a post authentication vulnerability 41080 instead of 41040. Very similar vulnerabilities, but different ones. Other than the .NET vulnerabilities that we've been seeing, we've also seen a rise of Java vulnerabilities that have allowed multiple actors to get access to network using Java program and Java software, not just .NET software as the .NET vulnerabilities. So we actually saw that the Apache Log4j remote code execution from the end of 2021 was the most exploited vulnerabilities in 2021 and in most of 2022 as well. You can see that in the 2022 Unit 42 Network Threats report, and more information about that is also available on our blog. But that vulnerability is still being exploited in the wild by multiple threat actors today to get access. Other than that, we've seen the Spring Core remote code execution vulnerability, or it's also known as Spring Shell. And we've also seen a Confluence remote code execution vulnerability that has been targeting that Atlassian framework. Another log4j, and so more. So there are a lot of different Java vulnerabilities, and those vulnerabilities, all of them have one thing in common. That's the Java deserialization concept. So to understand what that is, we need to understand what Java deserialization is and how it works. So basically, Java deserialization is a process where we can take a byte stream and then save it to disk or save it into memory and pass it along to a different computer over the network, and then serialize it back into memory, and then load that object in its original state to the software. So usually it's done in either JSON or XML formats, and it allows us to move data between devices or to save them on disk and so on. Java deserialization is doing this process specifically in Java, and it has two sides to the process. So, first of all, you take this object, you turn it from an object in memory into a byte stream. Then you either save it or move it to a database or over the network to a different location where that byte stream is serialized and deserialized and loaded into memory. Because Java is a platform independent programming language, we can execute that piece of code on multiple devices and multiple operating systems in multiple environments, while there is no need to compile a specific targeted exploit for each environment. If we're looking at the log4shell attack sequence, in that case, the attacker did use a deserialization vulnerability, and the attack sequence can demonstrate that. So, first of all, the attacker found a user controlled input that is logged using the log4j logging system. Once the attacker has that user controlled input, he can send a malicious GNDI URL to the victim device. Then the host sends a request to the attacker IP in return, which was provided in the original request. The attacker responds with the Java class to be loaded and executed. That Java class is malicious, and the JVM loads that Java class, executing the malicious code. Pwn, win, game over. Since in this specific case, the idea was to find a user controlled input. Once you found that type of input, you could provide your own code to be executed on any host that can actually execute the Java code. Another type of attacks that we've been seeing in the past year is driver abuse. Driver abuse is not a new type of scenario for attacks going into 2022. It's been with us for a very, very long time, but we have seen a rise in these attacks, and we have been seeing more and more threat actors using it in multiple different campaigns. The idea is that you can use a legitimate signed driver to abuse the Microsoft security module, allowing you to elevate privileges and bypass multiple security products. So, to understand the security model, we need to understand that Microsoft does not consider a process running in admin mode as breach of security. If you're running in admin mode and you got there because you're allowed to get there, this is okay. So when you're loading a driver, the driver by definition needs to have admin privileges. And that driver then allows you to get the kernel privileges to perform whatever activity that you want to do, such as killing processes, accessing memory space, etc. Um, since the drivers that the threat actors are using are benign and are signed by respected and very known companies, most security products or just products just treat them as benign because that's what those drivers are supposed to do. They're part of the system that installed them. So, for example, you can bring your, as a threat actor, you can bring your own vulnerable driver and drop it on the disk and then load it. And you will be able to load it because that is a benign driver that some other vendor, an example in this article, either Asus or Gigabyte, said that it's a good driver. um, because your process already loaded that driver, and it means that your process was admin. Your process had admin privileges, and now it has kernel privileges, allowing the process to do whatever you want. Another option for threat actors is not to bring their own devices, but to use drivers that already exist on victim machines. And multiple times we're seeing that when a software installs the driver for a legitimate use, and then a different process with lower privileges can escalate privileges by loading that driver and using the driver that's already loaded on the machine. For example, in this article, we saw a computer mouse from Razer that its driver allows users to become admin by just loading the driver inside. Once you buy that mouse, you install the driver on the system, the driver is now there, and now malware can use that driver to get that privilege and do whatever it wants. So we've seen a lot of this happening in the past year. We've even seen some of it in the past month with additional drivers being I wouldn't say compromised, more as used in attacks. And multiple ransomware gangs started using those techniques in order to get to targeted victim machines, load benign legitimate drivers, then disable the security products that are installed on those victim machines. And from that point on, it's game over. You don't have a security product any longer. And the ransomware software can do whatever it wants. It can encrypt your device and they win. The reason they can disable your security product is because they are an admin and they are the privilege and they're allowed to do so, which they should have because admins should have those privileges. The problem is that they shouldn't be able to load that driver to begin with. So the attack sequence in those abusable drivers is that there is some malware sample that's downloaded and executed on your device. Then that malware drops a driver to the disk. Not necessarily the driver couldn't be there before the malware arrived, but many malwares do bring their own devices to work and drop their vulnerable drivers, write them to disk. At the next stage, the malware loads that driver. Again, that's optional. Sometimes it's already loaded into memory and they can just access it. It would be a different attack scenario. In that case, it would be a vulnerability exploit. But most cases, they do load the driver because they need to load it. Once the driver is there, they basically exploit it and they bypass security measures. And when game over, they execute their objectives, either killing security products, abusing GPU resources, executing kernel code, and more and more. A very good example of those vulnerable drivers is the XMRig coin mining malware. It's actually a funny story. If you write XMRig and driver, you will get a GitHub page, and there is a complaint by someone saying, "Hey, I tried to install the WinRing Zero driver that is needed for the coin miner to be able to mine cryptocurrency on the device. There is a bug. Please help me fix this." The XMRig gang is using a legitimate benign driver called WinRing Zero and is using that to mine resource for cryptocurrency and abusing the resources of the targeted devices. Something they shouldn't be doing. So it's an interesting use case. Another thing we've been seeing in the past year is prevalence of hacker tools. We're all familiar with the question of hacking tools, are they legitimate or not? Should those be sold? Should those be considered malware and so on? There are multiple vendors that sell the different hacking tools to red teams to allow them to create their red team exercises and testing. And then there's also multiple frameworks that are developed and released as open source and for educational purposes only. Then the code is available on GitHub and stuff like that. But any tool that can be used for testing can also be used for hacking, because that's exactly the purpose of the tool. So there is a dilemma there. Who is this software sold to? How is it going to be used? Uh, is the vetting of the vendor that sells the software deep enough? And do they verify that they're not selling to criminals, and so on and so on? So, considering all of those issues, Cobalt Strike has been with us for a very long time. It's a commercial tool sold to security practitioners. The vendor that sells it has a very good vetting process. They check who they're selling the code to and who they're selling their tools to in order for those tools not to be used in attacks. Brute Ratel has been developed in the past year and gotten into the headlines, let's call it, and it tries to follow a similar selling and vetting procedure to be sold only to good red teams. But at the same time, Sliver and Manjisuka are less vetted. Manjisuka is a framework from China, so it's less tested, let's call it this way, and less vetted who's using it. And Sliver is just open source, so you can just go on GitHub and download it. The question of is this a malware, is this not, is a very big question in the security world. Most vendors and red teams think that those tools should be prevented, and we do put a lot of effort into preventing and detecting the usage of such tools. So, if we're looking at Cobalt Strike, it's a framework that has been with us for a very long time. It's not new. It allows for attackers or testers to put a beacon on your attacked platform and then start getting commands from a control server outside the network. We've seen this tool being used in multiple real life scenarios, such as Solar Storm, as Wasted Locker, Fin7, APT40, and more, where the actual framework is used by malicious threat actors to abuse and target legitimate users. The fact that back when Solar Storm was first published, we did manage with Cortex XDR to detect it. We detected the Cobalt Strike portion of the attack was the thing that helped us prevent the whole Solar Storm exploitation for our customer environments that were targeted with this framework. A similar framework would be Sliver. Sliver, as I've mentioned, also is a cross OS platform. It supports both Windows, Linux, and Mac OS. It's very customizable. You can change a lot of the different parameters and options that this implant allows for. And at the end of the day, its main goal is to be an implant on the target machine post exploitation to receive more commands and to do additional attacks. So this specific framework is open sourced, so you can just download it, compile it, and use it at will. Brute Ratel is, as I said, a newer framework, was released in the past year. We've seen a lot of different threat actors use this tool already to attack some of our customers. Again, similarly to Cobalt Strike, the vendor that sells this is trying to do some vetting on the customers who they're selling it to, but the software itself has leaked this, and it's if you search for Brute Ratel or Cobalt Strike, you will be able to download the servers and code from VirusTotal. You will be able to find a version and just execute it and use it to your own needs. So, considering the fact that anyone can download that tool and use it to do whatever they want, the whole aspect of vetting and making sure that it's not getting into the wrong hands is gone. It's very important for security vendors and device and protocols to be able to detect and ideally block the implant itself from doing anything after the after it's being loaded and not being able to communicate with the C2 server behind it. And in the past year, we did develop a new capability for shellcode detection that allows us to detect the shellcodes used by all of those different frameworks and prevent them from getting to the next step of the attack. Those are the four things that we've been seeing more and more in the past year, and we've been working a lot to enhance our protections and capabilities on the XDR agent to protect our customers. I'll quickly go over those capabilities. Every process that's being executed on the host will be tested in three different phases of its life cycle. There are several modules that are designed to detect and prevent malicious behavior pre execution. One would be the technique based exploit protection and prevention, which also includes the Java deserialization protection that allows us to block exploits based on the techniques. So, in the Java deserialization module, will allow us to prevent the Java exploits from the first section. It will also allow us to prevent the .NET exploits that we mentioned earlier as well. Then we have the kernel protection that prevents exploits that are targeting specifically the Windows kernel or the kernel in the every OS, not just Windows. We have threat intelligence capabilities allowing us to check every process versus a very large threat intel database telling us if that is a known malicious process. If so, do not let it execute. And we also have an AI driven local analysis agent and module that allows us to look at a file and its attributes and a process and its attributes and decide if that is a malicious process. If so, we will prevent it from loading and executing. If at the pre-execution stage we did not know and couldn't say that this process is malicious, we will upload the file that generated the process or the file sample to our cloud-based malware analysis threat emulation platform, which will execute the sample and in a sandbox environment and will let us know if it's malicious or not. And we will get a verdict from that platform and will decide to terminate the process if needed. Um, Other than the cloud execution, we also have the post execution modules that are looking at what the process is doing while executing. And based on that, we make decisions on the fly based on the execution. So the first module would be the behavioral threat prevention or threat protection, which is looking at all the different activities that the process is doing. For example, injecting into a different process or writing registry keys, making network communication, and so on. And if we decide that there is a combination of malicious attacks or malicious steps, we will prevent that process from doing additional actions. This behavioral threat protection also has a submodule that is used specifically for the vulnerable driver protection, which allows us to check if a process is trying to either write or load a vulnerable driver in order to do the next steps, as mentioned in a previous stage, of disabling security products or accessing GPU and so on. And the behavioral threat protection will prevent those drivers from being written to disk or loaded into memory, and thus will basically prevent the malware from getting to do whatever they wanted to do. We also have a malicious process prevention module that allows us to stop threats based on scripts that do not have specific hashes or files related to them. A ransomware protection that targets specifically the encryption part of the ransomware malware. We have the in process shellcode protection that is used to analyze specific shellcodes that are loaded into memory in process, and that allows us to detect in an earlier stage the different attack frameworks such as Cobalt Strike or Sliver, etc. And our network packet inspection engine, which allows us to inspect different communications going out from the agent to C2 servers and detect those if those are malicious to kill the process that created them and prevent further communication. If you'd like to learn more about Cortex XDR agent or Cortex XDR in general, you can join us for Demo and Dash. It happens every third Tuesday of the month. You can register on the link that's on your screen right now. We'll be happy to have you. Thank you. Again, my name is Irena. I'm Director of Research for Cortex XDR. You can find me on Twitter, on LinkedIn. I'll be happy to chat. Thank you.